Today I'd like to show you how to multiply polynomials. We've added and subtracted already. How do we multiply polynomials? And to start off, let's review how to use the distributive property. When you have a problem, when you've got a number multiplied by a group of things, remember we took that number and we distributed it to both of those things. I like to draw arrows, and that reminds me that I have to do 3 times x, which is 3x, and 3 times 8, which is 24. And I think you saw some examples actually where you can multiply a number by 3 things instead of just 2, or even 10 things. If there were 10 things in the parentheses, you would just draw that many arrows. So 3 times x squared is 3x squared, and 3 times 2x is 6x, and 3 times 8 is 24. So that distributive property is really at the heart of multiplying polynomials. Multiplying polynomials is really no more than distributing more than one thing. So here's an example. I'm multiplying 2 binomials together, and that will create a polynomial. And to do that, instead of just distributing the 3 to these 2 things, I also have to distribute the x to both of those things. So I like to do that by drawing a series of arrows. So I'll first start with this x. That x needs to be distributed to both the x and the 8 in this expression. When I do x times x, that gives me x squared. When I do x times 8, that gives me 8x's. And now this 3 needs to be distributed to both things. So 3 times x is 3x, and 3 times 8 is 24. So these 4 terms are my answer. Although there's one thing that we tend to do, usually when there are like terms, let's see, the x8, this arrow here gave me 8x's, and this arrow also gave me x's. Usually those 2 things are combined, and so our final answer would be x squared plus 11x's and plus 24. We could check that work easily enough by plugging in a number. Maybe I'll plug in the number 5. Arbitrary, I just picked a number. But if I plug in a number 5 for x here, 5 times 3 is 5 plus 3 is 8. And here, 5 plus 8 is 13. 8 times 13, why did I do that number? 8 times 13 would be 104. And then over here, if I plug in a 5, 5 squared is 25. And 11 times 5 is 55. And 24 is just written there. If we check this, 25 plus 55 is 80. And 80 plus 24 is 104. And so because those 2 numbers match, I'm pretty confident that we did this multiplication correctly. To really check it, I remember we ought to draw a graph. That's what we learned yesterday. So let me suggest a couple ways of keeping this straight. A pretty important concept is that whenever you do these multiplications, you need to make every combination possible. And so in this last example here, there were 4 combinations possible. I could do this thing times this, and this times that, this times this, and this times that. So one way that is commonly taught to describe or to remind you of all those 4 combinations is a simple acronym called F.O.I.L. If you've ever used the F.O.I.L technique, or if you've heard students in other classes perhaps talking about F.O.I.L. F.O.I.L is an acronym that indicates these 4 arrows. The first term in this polynomial and the first term in this polynomial corresponds, that combination is sometimes called the firsts. and then the outside most terms need to be multiplied together. Sometimes those are called the outside. The inside need to be multiplied together. So this term here and this term here, the terms on the inside. And then the last term in this and the last term in this have to be multiplied together. And so those four arrows conveniently form the word FOIL. And so some teacher a long time ago noticed that and used that, and it's kind of a helpful acronym. I don't really like it. I hate it, actually, because it really only works when there are two terms by two terms. And there's a lot more multiplications that are possible besides two terms by two terms. But some textbooks only give you 2 by 2s in your first year of algebra. And so I think that's why FOIL kind of caught on in popularity. I will probably never mention it again because it only applies for 2 by 2s, and I will give you some that are 2 by 3s or 3 by 3s, and FOIL doesn't work for that. There's 6 or 9 combinations to be made in those examples. So one method or one thing I like when I draw these arrows, I tend to think that these arrows they remind me of, say, a lobster claw, and so I'll often say use the claw. It kind of looks like little pinchers. So sometimes that helps. Another way that I've seen people draw the arrows is I've seen people draw this combination and this combination and this combination and this combination. And some people with better imaginations than me kind of think this looks like a monkey face. And so I've seen this described as a monkey face as well. Monkey face, really, like FOIL, only works with 2 terms times 2 terms. But still, it's just a way of remembering that every combination I can make, I need to make. So now remember, a combination means a term from this polynomial and a term from this polynomial. So I can't make this combination, for instance. Those 2 terms are in the same polynomial. I wouldn't multiply them together. But anyway, let's look at a few other examples, and then I'll show you one other trick or technique that I've seen a lot that I think is very useful and helpful for remembering all the combinations. So here's another example. It's 2 terms by 2 terms, and so it's a simple 4 arrows sort of drawing, just like the last one. X times x is x squared, and then x times -2 is -2x, and 5 times x, that third term, third combination, is 5x's, and then this 5 times -2 is -10. This is kind of our answer, except we would normally combine these things. So x squared plus 3x's minus 10 is our final answer. Over here, here's an example where FOIL wouldn't work because there are more than 4 combinations to be made. This x, for instance, needs to be distributed to all 3 items, all 3 terms in the second polynomial. And then this 3 needs to be distributed to all 3 terms. So if I were to list all these, x times x squared, sometimes I put little tick marks in there to indicate that I've thought about it. So x times x squared is x cubed. And then this next one, x times 4x is 4x squared. X times x, remember, is x squared. And then this third combination, x times -1, is -1x. 3x squared, that combination is, well, I just said it, 3x squared, that's all there is to that. 3 times 4x, that combination is 12x's. And then 3 times -1 is, the final combination we have is -3. And there's a little bit of combining that we can do here. Let's see, we've got an x cubed term, and that's it. So there's an x cubed term in our answer. And then there are some x squareds and some more x squareds. Those combine to give us 7 x squareds. And then there's an x term and an x term. -1 and +12 combines to give us 11 x's. And then there's a number term, -3. So the final answer to this, when we're all done multiplying and combining and so forth, is here. So the last thing I'd like to show you today is just these same multiplications, but using a slightly different technique called the table method. So a table method is a nice, helpful way of organizing all this work and finding all the combinations. If you've ever seen what's called lattice multiplication, you're a little familiar with the table method. Lattice multiplication works like this. If I was going to do, say, 13 times 48, typically you probably have seen it written like this: 13 times 48, and you do 3 times 8, 3 times 4, and 1 times 8, and 1 times 4, and, or 10 times 8. And really, you're doing very similar stuff. You're making every combination possible when you multiply that out. But the lattice method is kind of unique. It puts the numbers 1 and 3 on the outside of a grid, and then it puts the numbers 4 and 8, 48, on the top part of the grid. And each one of these boxes needs to be filled in. And so 1 plus 4, or 1 times 4 is 4. And 1 times 8 is 8. 3 times 4 is 12. And when it's a 2-digit number, you write a digit on this corner and a digit in this corner. And then 3 times 8 is 24. I'll write a digit in this corner and a digit in this corner. And that's kind of important because to get our final answer, then we add along the diagonals. A lot of textbooks teach you to draw in the diagonals right away so that you've got them in the right spots, and that's fine. That works too. But if I were to add all the numbers in this diagonal, that's the ones digit. And when I add all the numbers in this diagonal, 8 plus 2 is 10, plus 2 is 12, and I've got to carry a 1 into the hundreds, and 1 plus 4 plus 1 is 6. So the answer to 13 times 48 is 624. That's lattice multiplication. If you've ever seen that, this method is basically the same thing. If you haven't seen that, it's okay. I think you'll still catch on to the method pretty easily. But that's kind of a cool way of multiplying things that I remember being in awe of the first time I saw it described to me. So anyway, to do the table method for multiplying things, you start by drawing a table. That's like we had the little 2 boxes by 2 boxes and so forth. And then you list our factors on the side and along the top, just like you saw with the numbers a second ago. You multiply to figure out those inside boxes, and then you combine like terms. And just like in the lattice method, for multiplying numbers, the common things that you add together end up being lined up along the diagonals. So kind of convenient. They're all nice and organized and neat. You don't have to go looking for them. So let's look at our examples. We just had x plus 5 times x minus 2. And to use the table method, I'll start by drawing a 2 by 2 grid. And I will list along one side the one of the factors, and then I'll put along the other side the other factor. So notice each term is associated with a specific column, and each term in this is given its own row. And then we multiply to figure out what each of these 4 things is. That's essentially what the arrows used to be. So x times x is x squared, and x times negative 2 is negative 2x. 5 times x is 5x, and 5 times negative 2 is negative 10. I kind of like this method because you're not going to forget a combination. If you were to forget a combination, there'd be a big gaping hole in your table, and you wouldn't do that. You'd see that there's a hole, and you'd do that combination and remember it. But then to combine things to get our final answer, notice the x's that can be combined. They're all lined up along this diagonal. So x squared, that's the only thing in its diagonal, so that's just part of our answer. And these things combine to give us our 3x's. And then this negative 10 is the only thing in its diagonal. And so that's our answer. X squared plus 3x minus 10. So, oops. To do our other example, x plus 3 times x squared plus 4x minus 1, I'll start by drawing a table. And I will list along the side, perhaps, the x and the 3. And then I'll list along the top the terms from our other factor. And here, this factor had 3 terms in it, so I kind of ran out of room. That's easy enough to fix. You just add another column. So instead of having a 2x2 table, you've got a 2x3 table. And just like before, now that we've got our table set up, we multiply. X times x squared is x cubed. And x times 4x is 4x squared. And x times negative 1 is negative 1x. And 3x squared, notice this is the x squared diagonal. This is the x's diagonal, so this term is going to be x's. 3 times 4x is 12x's. And this is the numbers diagonal. And there's patterns to it. When you do this often enough, you'll see this is the constant term, and here's where the linear terms show up, and here's where the quadratic terms show up, and here's where the cubic terms show up. It's very consistent and systematic. So, and I can get my answer by combining those different things. This first diagonal is just x cubed. This diagonal is 7x squared. Make sure you actually put in plus 7x squared. And then this is 11, so plus 11x's. And this diagonal is just negative 3. So there's our answer. Get each of these circles by figuring out what their diagonals added up to. So there's multiplying polynomials, both using what I call the arrows method and also using the table method. So thanks for watching, and be sure to tune in next week as we talk about undoing this with a process called factoring, where you're told the answer and you have to figure out what were the original things we multiplied together to create that.